Hello all, this is Muhammad Anif from RGKT Basar. I once again welcomes you on this digital signal processing lab. So today we will see the filter applications. So here I do have three tones. Each tone is mixed with some noise. Okay, so first we need to identify the where the frequency component is available and the where the noise is available, and then later we have to choose the exact or required filter to remove that noise. Okay, so let's start. Starting with CLC, clear all, close all, and we'll try to read these audio files here. So for that one we am taking one variable x1, and then every audio file is consist of some sampling frequency. So for that one the sampling frequency is written as fs here, and then with the function audio read we can read the audio file. So I'm reading this tones 1 at mp4. Okay, and then we will play this sound x1 fs. So here we do have a 10 seconds of tone. You can if you have observed that, you can understand that it is corrupted with noise. Okay, and here you can see that we are able to able to find the value of fs, which is given as 44,100, and then x1 is having 4 lakhs, some 4 lakhs change rows. So now first we'll try to find out where this frequency components available in x1. Okay, so for that one we need to find the FFT of x1, and then we'll plot that, then so that we can able to see the frequency components. Okay, so first we'll take we'll try to here you can see that x1 is consist of many rows. First we'll convert this into single row. So for that one we'll do x1 transpose. Okay, and then we'll find the FFT. Now FFT will save in x, so FFT of x, and then we'll try to plot absolute value of this xs. Now here you can see that first we have done transpose of x1, so x is now transposed and with one row, and then columns have increased to this 4 lakhs change, and then we have calculated the plot FFT of x, and then we have plotted it. So this is the plot. Now with by seeing this graph you can see that this is the noise available, and these two are the frequency components. So by seeing that we can see we understand that we need to get this frequency component, and then we don't need these frequencies, and then we need this frequency. That means we can go with a band stop filter, so that it will stops these frequencies, and then it allows these two frequencies. So this is we can employ, or we can use a band stop filter to remove this noise. Okay, so first of all we need to identify the frequencies of this one. So these are filter coefficients. Okay, so now first we'll take a marker, and then we'll put on here so that we can get a frequency of that. Now here it is showing that on x-axis it is displaying 5005 for the first spectrum, and second spectrum is given as 6 into 10 power 4, that is like 60,000. Okay, now first we'll calculate this where the frequency is available for us. So for that one we know that digital frequency is given as The digital frequency is given as 2 pi 2 pi f upon fs, sampling frequency. So this is digital frequency radians per seconds, radians per samples, and then this is our analog frequency, right? And if you calculate the FFT, and then if you do the samples for, actually we do have uh, 0 to pi, sorry, 0 to 2 pi for radians, and then if you do sampling for this for on every second, like the on 2 pi n, and then this is the coefficient, then omega k is given as 2 pi k upon n. Now we will equal this one together, and we will try to find out the frequency for our filters. Okay, so these two will get cut off. Now f is given as k in fs by en. Okay, now k is first k is, so this is the, so first this is the k, so here it is given as 5000, so I am writing 5000 multiplied by fs is 44,000, and then n is this one, the total number of samples. Total number of samples is around 44, 4 into 10 power 5. So 4 into 10 power 5, so we'll write 40 into 10 power 4. So we assume that this is nearby this 44, and then we'll cancel these together, and then here we'll get another 10, and this 10 if you cancel with this one, so first cutoff frequency we understand is 500. Similarly, we'll calculate for the second one, so second cutoff frequency, so that is k2 fs upon n. So here k2 is now around so this is 6 into 10 power 4. Six into 10 power 60 into fs, this is 44 into 10 power 4. So once again this is, so we cancel this together, and then 10, so 10 means we'll cancel this, so this is 6k, 6000, right? So now we found that there are two cutoff frequencies. One cutoff frequency is at 500, that we do have one frequency component at 500 hertz, another frequency component at 600 hertz. Now we need to design one band stop filter. So for that one I'm using the previous program which I have already explained you in my previous videos. So I'm copying that entire program in new file, so I will be writing one function here. Okay, function for small h, and as we need band stop filter, so we'll give name that as a h band stop filter, right? And here we need some coefficients, so so this is the band stop filter, and we'll end the function with end. here in this one we need to enter the filter coefficients length, enter the odd number. So here we need to enter the L value. So enter ordered number, filter impulse response, right? This is for okay. And then here as we are entering this one, so you do need of fs, so we'll write a component as fs. So we are we are taking this band pass filter entire program as a one function, and we are naming that as hbs. So this is the function starting, and then we are attributing with to small h. Okay, and this we are ending. So we'll save this first. So here you can see that this is the function program, and now here we'll write calling band stop filter. So we'll call that with small h is equals to hbs and then sampling frequency, right? And then so this actually this program is consist of only filter coefficients for band pass filter. So now after to make it as a complete filter, what we have to do is we need to do convolution. Okay, convolution with x and h, and I will save this in as a output tone, right? And then we'll also write sound output tone fs, or else we'll first stop this and then we'll calculate x1s is equals to f50 of output tone, and then we'll plot this. Right now so this is the first one. It is showing that this is noise is available here. So we have calculated the cutoff frequencies. We have calculated the frequency components. The first frequency component was 500. So we'll give as it is, it has to pass. So we'll increase the cutoff frequency to 1000, and then upper cutoff frequency. So our frequency component is available at 6000. So we'll give upper cutoff frequency as 5500, and then the length of the filter is will give as 555. Okay. So once again I'll run this program. So here you can see that we have successfully able to remove this noise here. Now we'll try to play this. Okay, once again running the same code. So here you can observe that we have successfully able to remove that noise. Okay, similarly we can do for remaining we can calculate for remaining tones also. Now we'll check what is available in tone 2. Okay, so I'll remove this, and okay, so now here in tone 2 the frequency components are start from here to here only, and the noise is available after that. That means here the best filter we can use is a low pass filter. Low pass filter with the cutoff frequency of after the second one. So you can how we can calculate that cutoff frequency by putting this marker here, and then so it is giving 5 into 10 power 4. That means around 5k will be our so below 5k both the frequency components are available. So we'll design one low pass filter with a cutoff frequency of 6000 will work for us for tone 2. Similarly for tone 3, now if we see, now here you can see that the noise available at the starting point only, and if we see this frequency component, so it is 5 into 10 power 4. Again the frequency components are started from 5k. That means here we can we can use high pass filter with a cutoff frequency of 4k. So that means it can pass the 5k and then second frequency component. So we can get our frequencies. Okay, so you try these two codes, or you try to make a one write a program such that it consists of many frequency components are there in that. Okay, so here we are first checking, and then we are calculating where the frequency component is available. So what is we can do here that uh, having some frequency components, and automatically we have to write a code such a way that automatically it identifies the where the frequency component is there, and then we'll keep every like one band pass filter there, so that we can extract that frequency component from there. Okay, I hope this video is useful to you. Thank you.